When we finished up the lab project, the last lab project, which would be the video before the last one, and the last one we actually talked about the hardware learning stations and basic atomic data types. This logic you see in front of you is the way we left that project, other than the fact that I had 6 rungs and each rung had an input bit turning on an output bit. Here I've edited those 6 rungs into 4 rungs as was shown in the manual, just for those of you that don't have more than 4 outputs but you want all 6 inputs involved. And then we specifically used this logic to discuss logical statements. If you are a programmer of some other languages, text-based, then you immediately see this logic in terms of a text string. For instance, the first rung, rung 1, says if in.0 and if in.1, then out.0, or it would say if in.0 and in.1, then out.0, else not out.0. The thing to understand about the OTE instruction, that it has a true and a false execution. So if the rung is true, it turns on the bit. If it's false, it turns off the bit. That is the then-else part of a text-based language. Logical statements always start with if, and remember that the syntax of the language is up to the developer. In most cases, instead of saying if in.0 and if in.1, then out.0, else not out.0, they will leave off the second if. In other words, they'll just say if, that would be the rung header right here. If in.0 and in.1, then out.0, else not out.0. If these were true if off instructions, with the slash through them, then it would be if not this. It wouldn't be just if this. The language is rendered down to the minimum amount of text to make it easier to type in. They've made it less wordy, but it's still understandable. The second rung is if in.0, then out.1, else not out.1. If in.3, then out.2, else not out.2. We don't have to do that in our code because in OTE it's implied that if the rung is true, the rung in is true, then this turns on that memory location. If the rung in is false, then it turns it off. So the then else is included as a true to false execution. We just want to do a quick little review of how we left that logic in our last project. Our next project, which we're going to start now, is the garage door control circuit. Garage door opener, probably one of the most common applications for learning to program a PLC. Everybody knows a garage door, has operated one. Garage doors are very easy to understand. On the left, you see segments of the garage door with pivot points, and you see a dashed line, double dashed line, and that represents the track that the wheels run in. You have a motor, 1M, and then you have a chain, a darker dashed line, that goes to a bracket on the door, and the motor, if you like, has a capstan that winds up the chain, pulls the door up, and what stops the door once it gets up is the edge of the door hits limit switch 2. Now limit switch 1 is actuated when the garage door is all the way down. In the past, someone has remarked, well, shouldn't the limit switch, one limit switch, be all the way down at the bottom of the door? You don't have to hit the limit switch with the bottom edge of the door. You can have a ramp up at the top of the door that doesn't engage limit switch 1 until the door is all the way down, and that's usually adjustable. That same ramp you'll see the little wedge there that could have a double ramp, in other words, in both directions. That one also operates 2LS, limit switch 2. The garage door, knowing whether it's all the way open or all the way down, is given to you through sensors, 1LS and 2LS. We're using limit switches because that's typically what you have on a real garage door opener. You also have a safety photo eye, 1PE, at the bottom of the door. I show it vertical, but that was the only way I could effectively draw it. But if you've looked at your garage door, at the bottom of the track, you're going to see a photo eye on one side and a reflector on the other side, or you're going to see a light source on one side and a photoreceptor on the other side. What I'm showing you here is reflective. It could also be a through beam. Through beam's probably the most common. On industrial garage doors, maybe not. You also have push buttons to control it. A button to tell it to go up, a button to tell it to go down, and a stop push button. You also have a lamp that illuminates the area behind the garage door, or you could say inside the garage. Alternative one, where you have one push button that can do up, down, stop, and do the whole thing. We're not going to do that one. These are your elements right here. You have two outputs, the motor and the light. For inputs, you have the up and down limit switches, the safety photo eye, and 3 push buttons. We're going to write logic to control this garage door. A quick review of what we did with this project. Remember that the goal of this project was to buffer our I/O. So we had a buffer inputs program, and it buffered 6 input module defined data types into bits of an integer named IN for N. Now we could have made it input and then .0, .1 and so forth, but in an effort to keep the tags as short as possible to make the screen and the logic less cluttered. You know the old saying, less is more. We also had our outputs buffered, meaning that the bits that we actually turned on and off with our logic then were buffered to the real module defined output tags, and then of course we had the sequence that you see here. So the first thing we're going to do in our garage door application is first I'm going to show you another scheme for buffering your I/O that looks a little closer to our application. So I'm going to pause, go offline, and then we'll start editing our existing code. I'm also going to rename this project once I get offline. Here we are offline with our buffer inputs program. We're going to do something slightly different. Remember that IN.0, IN decimal point 0, is just a bit in memory. And although it is one of 16 bits that make up a 16-bit integer, it's probably one of 32 bits of a dent of which is being used up for a single integer. Not an SINT, I'm sorry, but an INT. In other words, they're only using 16 of the 32 bits. With memory being as inexpensive as it is, that's the trend. In control logics and compact logics, the native data type is dent, double integers. So if you create a Boolean, a single Boolean, you just used one bit out of 32 and the other 31 are hanging in the breeze and they will not be used. If you follow along what we did in the manual, I'm going to try it in a different way. I had you actually open the variable selector and do it from there, but instead I'm going to click there and I'm going to type in IN00. And well, we use capitals. I'll do that just so it looks just like the book. That's interesting. It's not letting me type that in because it thinks that I want the existing tag IN. If I backspace and do a uppercase N, it goes in as a lowercase n. That's interesting. So we'll go ahead with that for now and see what happens later. It comes up and it says that's a name, but it's not a tag because IN00 doesn't exist yet as a tag. It has to be defined. If I went to variable selector, let me see if it will let me do it here. Backspace N, and it does. Interesting. I'm going to say OK, and now it's capitalized IN00. I'm going to go back to variable selector now that I have that tag, and I'm going to put in the alias. And the alias for input 00 was PhotoEye safety, PE underscore SAFETY, PhotoEye safety. You could put in safety PhotoEye. However, what I've found is when you're looking for things in your program, you're usually looking for a type and then a specific of that type. So I tend to put PhotoEye first and then the specific, rather than the specific then the PhotoEye. Because if I put safety in front, then when I go to look for the tag or look for the object, everything that begins with safety is going to show up. However, if I'm looking for a PhotoEye, I just find it easier to put the, if you want to call it, the adjective after the noun. And in some languages in the world, that's what they do. The adjectives follow the noun. So I'm going to say OK. Now you see we have digital input 0, the actual module defined data type that's controlled by the toggle switch, or in this case it would effectively be a PhotoEye out there at the bottom of the garage door, the safety PhotoEye. It's input 00. Now remember that we don't need both of these. Input 00 and PhotoEye safety are really the same thing, but they're two separate tags, so to speak. One's a tag and the other's the alias for. We could have put them in the reverse order and then had PE safety on top and IN00 on the bottom. I chose to do it this way because when you are searching for something, typically it's a match with a print, and on your print it's going to be an input. But for right now, we're just going to leave it simple like this. If you look at the manual, and I'm interrupting this lab to point out a variation in what we did in the videos versus in the manual. If you look at the tag names and aliases in the manual, IN00 is PhotoEye safety. We have, instead of having the up push button, in other words, if I go to approximately page 108, you see that I have the up push button input 01, and here it's the down limit switch. So in the video, I'm using different aliases than I did in the lab book. Now this shouldn't be a problem because this is the function right here. This is almost irrelevant, and it can vary from one project to the next. It's the function that matters. Just make note that when you're watching this video, the IN0X may not or will not match what's in the manual. As long as you know that up front, you shouldn't have a problem. I'm going to add one more. I'm going to double click here and type in IN00. I'm doing this for a reason. Now I'm going to select variable selector. I'll cancel that. I'm going to see if I can get away with doing it right here. Single click, click, backspace 1. Okay, it let me do it. Now I'm going to go to the variable selector and say OK. So it appears going directly to the variable selector in the first place is probably the fastest or the quickest method. And this should be down limit switch. So DOWN underscore and then LIMSW. We're using uppercase, lowercase, and underscores to try to make it easier to read. So I say OK. Now you see input 0, input 0, input 1, input 1. There is another way that we can do this that is less cumbersome. Go to global variables, double click. There you see two that we're not using anymore. We'll leave those in there for now. And the other ones that we added went to the local. If we go to buffer inputs, local variables, there you see the two that we added. So now we have the debate of whether they should be in local or global. Well, I can answer that emphatically. They must be in global, because the local variables for buffer inputs program are only available for use in the buffer inputs program. You can't use them in the sequence program. So our buffered inputs and outputs, those tags must all be in the global variables. I'm going to move them. I'm going to click on this, Shift. Now I have two selected. Control C, go to global variables, go down to the bottom, click here, Control V. Just like you would with the word processor. Now I'm going to go back to the local variables, and I'm going to delete these. Now they're not in the local variables. We didn't do any tags in the outputs yet, so I just double clicked and opened on the buffer outputs variables, and there's nothing in there. And now when we look at the buffered inputs variables, there's nothing in there. If we look at the sequence, there's nothing in there as well. Now there are tags that we can put in sequence, but if we put them in the sequence local variables, they will not be available to any other program except the logic that's in sequence. Go back to the global variables, and there's the two that we added. We could, from here, start creating IN02 and then alias right out of the book for 02 is up limit switch. UP_LIMSW. Enter. See, now we have created this tag in the global variables. We could go through and create all of our tags right here and then do the logic. That's what I'm going to do. I'm not going to make you sit here and listen to me droll on about creating all these tags. I'm going to pause, create them, and then come back. Now we have all 6 created. IN00 through IN05. Photo-eye safety, down limit switch, up limit switch, stop push button, up push button, and the down push button. So now let's go edit our buffered inputs. And this is not a tag. So it appears that it's not a tag. I'm going to reselect it. See, so because we did this kind of in a roundabout way, we crashed this logic. I'm going to go to here, double click. See, now the warning is gone. So I'm going to go to variable selector and click, and now it's fixed. Now we'll just try typing in IN02. See what we get. Okay, see, we got the whole thing. IN. Actually, if you've not worked with any program before or any programming language before with a PLC, you're going to have an easier time than those of us that have thousands of hours experience with RS Logix 5, 500, and 5000, because we're accustomed to doing things a certain way, and we're going to keep trying to do that even though you can't do that with Connected Components Workbench. IN04, enter, and IN05. Okay, now we're buffered. The same module defined tags now buffer to these new tags. And remember, the reason that we did what we did here by making the tag input 4 alias to up push button was to make it display this way. It's not going to make any difference in how it operates whether we had input 4 on top or up push button on top. Actually, if you want to, you could go back and do it. So up limit switch is the tag alias to IN00, and then you'll see it flips around. So the tag that we're using, input 2 to input 2, but then we're aliasing it to up limit switch. Let's go do the outputs. Go to our buffered outputs, And these are the tags that we're going to be changing. However, we need to go back to our global variables to do this. So rather than even start here, let's just open global variables and go down here and start putting in those tags. So the first one in is OUT00, and then we're going to alias that to motor up, MOTOR underscore, and then capitalized UP. We hit enter, that tag's created. I'm going to finish up these tags and come back. I'm going to pause, finish the tags, and come back. Now you see I have all 10 tags created. However, we have a motor up and a motor down and a light. We don't have any other outputs. As a matter of fact, the reason we're doing motor up and motor down is because we are using a reversing contactor. There's a bunch of different ways that you can run a motor in two directions. We just picked one. Now there's a whole section in the manual, a couple pages, that discuss the garage door opener, and it discusses contactors, motor starters, and it has the electrical diagram equivalent to controlling this garage door. In other words, if you were going to do this electrically, I show and discuss the schematic in the manual on approximately page 101. So you need the manual in front of you most of the time when you're watching these videos, and maybe even your training station so you can follow along. Maybe you want to do the labs yourself, then start over, watch the video, and then watch the video again doing the lab again. You cannot spend too much time repeating this stuff. Typically they say it takes 10 times hearing something or seeing something to remember it really well. Now let's go edit our buffer outputs. This is what we want to buffer right here. This is what we want to edit. So I'm just going to type in OUT00, enter, and you see I've got the whole thing. OUT01, OUT02, and OUT03. And of course, we're not using OUT03 or this output here. Later on in the labs we will. Matter of fact, there'll come a time when we could use even more outputs and inputs if we wanted to show everything. In some of the later applications, that particular application and challenge is in the second half of this document. Remember, the manual was broken up into two separate pieces, separate bindings, just for ease of handling. So there we have our logic, our buffering. Now if we go to sequence, we no longer need any of this logic. So I'm going to delete all of that logic, and I'm going to save. We'll start working on the logic and sequence now that we have everything buffered. In the manual, I had you, before you deleted any logic and sequence, I had you open it up so you could see the changes that took place in the sequence. But I'm going to skip all that. You can read through that in the manual if you like, and I'm going to start right out and create a rung of logic to control motor up. Obviously, we need a couple things. We'll start with the classic start-stop circuit, and then we're going to modify it to fit what we actually have. We need if we were doing this electrically, we would put in a normally closed. I'm going to cancel because I'm just going to type in the tags directly. Then we would need a normally open contact, and we would need a coil. And then we need to bypass the normally open with a branch around. And then we need a seal-in contact, also normally open. So I'm going to go ahead and assign tags to this. This would be the stop push button. This would be up push button. It's going to be up or down. In other words, we need an up and a down circuit. So we'll start with the up push button. And then this would be motor forward. And I think we named it motor up. So MO motor up. And then we also need the same tag here. If this were an electrical circuit, this is a normally closed push button. So that means right now it has continuity. This is a normally open push button. So if you're not pushing the stop button and you push this button, this closes and it energizes the motor up. And if the motor up is energized, then this goes closed. That way when you let go of the up push button, this contact seals in that contact and the motor continues to run up until you push the stop push button to break the continuity. Now we're doing logical continuity, not electrical continuity, but it's really one and the same thing. Now we do have a major deviation here, and that is we use a normally closed stop push button in the electrical circuit because if it breaks or the wire opens, the motor's not going to run no matter what because it's open. However, if we want to use a normally closed push button so we have fail safe, then if that push button is not pushed, it's a normally closed push button and it's attached to input 3, then input 3 would be on in the safe condition, the non-stop condition. So that means that we have to replace this with a normally open symbol. I'll delete this one. There we go. This says if the stop push button is not pushed. In other words, we're going to use a normally closed contact for our actual stop push button on our field device simulator because we want this fail safe. But we're going to use a normally open for the up and then a normally open for the motor up auxiliary contact off of the starter. So let's save this, and you notice that I named mine M850 buffered because we have buffered IO, garage door 01 because we may have more than one iteration of this program. So I'm going to save and then download, and while it's downloading I'm going to pause and go offline and then come back. Okay, downloaded and online, and you notice the rung is false and none of the instructions are true. Now keep in mind that if this is what you saw in a real system, this would imply that someone is pressing the stop push button because the stop push button instruction, input 03, alias to stop push button, is not true. And it should be true unless you're pushing the button. I'm going to flip that to the on state, and I've also momentarily pressed input 4. I'm going to momentarily press input 3, but long enough for you to see the true-false state of that first true if on instruction change state. So I'm going to go to input 3, press the button, you see it goes blue, false, and when I release it, the instruction that looks at the stop push button is now true again, but the rung has gone false and the else part of that OTE has set output 0 to off. If I momentarily push the input button, which is input 4, and I hold it down so you can see it turn red, then release it, you see it's false, you see it seals in, because once we have the motor running, when the logic comes and reads, when you're scanning the logic, it reads the stop push button is on, so that's and not pushed. It's not pushed, therefore it's on. Continuity. So input 3 is on, so that instruction is true. Then it looks at input 4, that instruction is false. Or it looks at output 0, which is true, so then it turns on output 0. In other words, they call it seal in logic. It seals in the momentary condition of you pressing the up push button. Just to remind you that if this processor is scanning 4,000 times a second, then 4,000 times a second it's reading this rung and turning on output 0. If I push the stop button, I pushed it fast enough where you didn't see it go from red to blue and back to red. But believe me, the controller saw it. So right now, if that logic is scanning 4,000 times a second, then 4,000 times a second it's telling output 0 it's off. These bits don't know that they're on or off. The logic doesn't know really if it's already on or already off. So if the rung is false, like it is right now, then every single program scan, that OTE that addresses output 0 motor up, it tells that location of memory that it's off 4,000 times a second. If I press the up push button, I'll do it fast enough that you won't see it change on the screen. Now it's telling that memory location, OUT00 motor up, it's telling it 4,000 times a second that it's on. If I go to the buffer outputs, you see that this is the bit that we're turning on 4,000 times a second, and when it executes the third program here, buffered outputs, it's telling this bit 4,000 times a second it's on. If we go to buffer inputs, the only input that we have on is a stop push button, because remember, that's a normally closed push button and it's not being pressed. If I wanted to toggle one of these off, it would effectively be the same thing as pressing the stop push button. Let's press the up button again. Now you see the motor's running. If I right click on this bit, now remember, this bit is being controlled by an input. See, it didn't actually do anything because I changed it to 0. I toggled it to off and it went right back on before it could affect anything. So toggling a bit on or off that's controlled by an actual input is not going to do anything. Output's a different story. For the rest of that particular lab, we exercised this single rung of logic quite a few times. Pretty much exhausted it in terms of looking at it from different angles. I'm not going to spend a bunch of time going over this. One thing I did do was I shifted the position of the stop push button just to show you that it really didn't matter whether it was here or over here. It logically is in series with the rung. Whether this instruction is here or over here, it's not going to make any difference. As a matter of fact, some people draw it that way. They put the stop button over here instead of first. Logically, it doesn't make any difference because it's if this and this or this, then that. If we move this over to here, then it's if this or this and that, then this, else. We also have a couple pages in there for RS Logix users. And we have a looks like a Micro800 data table. Now, if you are a RS Logix user, then we don't need to discuss this because you know exactly what's going on in that little demonstration. If you are not an RS Logix user, then it's irrelevant and we don't need that section anyway. So we're going to move on to more start-stop logic in the next section.